Have you ever stared at a vast, intricate circuit diagram, wondering how you could possibly analyze the behavior of just one small component connected to it? It can feel overwhelming, like trying to map an entire city just to find one address. Fortunately, for circuit analysis, there is a powerful simplification technique. The Thevenin equivalent circuit is applicable whenever you need to analyze the behavior of a specific part of a larger, linear electrical circuit. It allows you to replace any complex combination of voltage sources, current sources, and resistors with a much simpler equivalent comprising a single voltage source and a single series resistor. This is particularly useful when the load connected to the circuit changes frequently, as it saves you from reanalyzing the entire network each time. The core reason this simplification works lies in Thevenin's theorem itself, which states that any two-terminal linear circuit can be represented by a single voltage source, known as the Thevenin voltage, and a single series resistance, called the Thevenin resistance. The critical word here is linear, meaning the circuit must consist of linear components like resistors, and the sources must also behave linearly. This linearity ensures that the principle of superposition and Ohm's law can be universally applied, forming the mathematical backbone for calculating the equivalent components. To practically apply this, you first identify the two terminals where your load will be connected. Then, you calculate the Thevenin voltage by finding the open circuit voltage across these two terminals, essentially removing the load and measuring. Next, you determine the Thevenin resistance by looking back into the circuit from the terminals, with all independent voltage sources short-circuited and all independent current sources open-circuited. If dependent sources are present, a different method is used, often involving an applied test voltage or current. Understanding the Thevenin equivalent also grants you an insightful perspective, closely related to Norton's theorem, which offers a current source and parallel resistance equivalent. These theorems essentially allow you to black box a complex part of a circuit, reducing its complexity to just two components. This concept is incredibly valuable in fields like power systems, engineering for load flow analysis, or in amplifier design for understanding source impedance, providing a shortcut to predicting how various loads will interact with a given circuit. Ultimately, the Thevenin equivalent circuit is an indispensable tool for simplifying complex linear networks, enabling quicker and more intuitive analysis of circuit behavior under varying load conditions. It transforms daunting problems into manageable ones, providing clear insights into the voltage and current characteristics at a specific interface, making it a foundational skill for any electrical engineer.